Today we are going to be looking at Newton's law of universal gravitation. Really, if you think about it, one of the things that possibly started it all, right? You'll have two formulas today, so make sure you have that handy. In today's discussion, we are going to explain how Newton's law of universal gravitation accounts for various phenomena, including satellite and planetary orbits, falling objects, and the tides. And then we're going to apply Newton's law of universal gravitation to solve problems. Question?
Yeah. So I have like this talking about like orbits and whether or not the perfect circle.
Elliptical.
Is that more like the moon orbits?
I want to say, is it? I don't want to give an incorrect answer because in the next section we start talking about orbiting objects where it does show elliptical, and I want to say that there are some that are circular, but others that are not. Okay, but that's
So I should actually
Google. All right, so as we probably already know, orbiting objects are in constant free fall. And so to understand, why don't you go there? Get an idea of what's going on here. Newton developed a thought experiment. And he says, what if there's a cannon sitting high on a mountaintop, way up in the air? What would happen if after each time I launched a cannonball, I would increase the speed of that cannonball, and by doing so, I would increase the horizontal distance that cannonball would travel. So as you see here, we have, this was just a thought experiment. This didn't actually happen. He stated that eventually, if given enough speed, that cannonball, due to the curvature of the Earth, would remain in the air without ever coming down. It would be in constant free fall. And so I started thinking about why would this occur? Or could it occur? And so he thought, as he was thinking about this, about what's happening with our planets, with our satellites. And when we say satellites, we're talking about artificial as well as natural, meaning the moon. Moon is considered a satellite. So when we're talking about forces, we can think about centripetal force and how it relates to gravitational force. Again, that whole apple and tree story, which many people say is not true. As we see that apple fall, it's falling towards the center of the Earth. So what gravitational force is, it's a mutual force of attraction between particles of matter. And it has a few factors that we need to remember and take into consideration. The masses of both objects, as well as the distance between the two objects. So we get this formula developed by Newton called the law of universal gravitation. So on your formula sheet, you want to make sure that not only do you jot down the variable formula, but also the word formula, as well as the constant that is present in here. So Newton's law of universal gravitation states that the force of gravity is equal to G, which is the universal gravitation constant, G times the product of mass of the first object and the mass of the second object divided by the distance between the two masses squared. Now, we don't necessarily have to concern ourselves with this part yet. But in the next section, I believe, when we start talking about satellites and other bodies like that. See, it's all about the radius. Well, you're going to be talking about the radius of orbiting bodies. And so we have to consider the distance, not only between the two objects, but between the center of the orbited object and the surface. And so there's going to be a few extra things that we have to do in the next section when we start calculating planetary motion. We get that down. All right. So the gravitational forces that two masses exert on each other are always equal in magnitude and opposite in direction. And so we have an example of Newton's third law. The Earth-Moon system is a prime example. As a result of these forces, the Moon and Earth each orbit the center of mass of the Earth-Moon system. And since Earth has a much larger mass itself, the center of this Earth-Moon system lies within the Earth. That's why the Moon orbits the Earth. Now, not only do we apply Newton's law of gravitation with objects that are falling, but also the tides. Okay? High and low tides are partially due to the gravitational force that is exerted on Earth by the Moon. And the tide results from the difference between the gravitational force of Earth's surface and at the Earth's center. So let's learn a little bit about the ocean tides from this guy.
Hey, check out our new test tube app in the iTunes store. Download it, give us a rating, let us know what you think, okay? Okay. Hey there, I'm Josh Clark, and in this Brain Stuff, I explain to you how the tides work. Have you ever seen somebody buried up to their neck in sand on the beach, and then the tide slowly comes in and they drown, and wondered, I wonder how tides work? Well, next time, you'll know, and you can explain it to that person as they wait to die. We need to be very careful here, because as French astronomer Francois Arago once said, studying the tides is the tomb of human curiosity, which means it can break your brain, as you'll see. There's a lot of factors involved in creating the tides here on Earth, but the big three are the Moon, the Sun, and the Earth. The gravitational pull of all three of those bodies interacting creates the tides. The biggest factor actually is the Moon. It exerts about 2.2 times more power on the tides than the Sun does. So for once, the Moon gets to one-up the Sun. It's kind of a big deal to it. Imagine for our purposes, the Earth is right here, and the Moon is directly above it. Now, they exert a gravitational pull on one another, and since on the Earth, most things are pinned down, we have shoes, buildings have foundations, stuff stays in place. But the oceans, being literally fluid, actually can be pulled toward the Moon, and this is what creates the tide. The Moon's here, is pulling on the ocean at the top of the Earth, creating a high tide on the top. Now on the bottom, another high tide is created because the Earth itself is pulled toward the Moon, even though the oceans down here have less gravitational pull exerted on them, being farthest away from the Moon. So on the top and bottom, you have high tide because of the tidal boldness, and on the sides that are at right angles to the Moon, you have low tide because the ocean's stretched thin over the surface of the Earth. Pretty crazy, huh? So, like I said, the Sun also exerts an influence on the tides, but it's less pronounced than the Moon. See, it actually enhances or diminishes the gravitational pull of the Moon here on Earth. When the Sun and the Moon are in alignment, the Sun enhances the Moon's gravitational pull, creating higher tides than normal. They're called spring tides, and they happen on a full moon or a new moon. Now, when the Sun and the Moon are at right angles to one another, with the Earth right about here, the Sun diminishes the gravitational pull of the Moon on Earth, creating lower than normal high tides, also called neap tides. These happen on the quarter moons. Because the Earth and the Moon are constantly moving and moving around one another, there's a constant movement from high tide to low tide. Twice a day, you get a high tide in most places, usually once every 12 hours and 25 minutes. But this can vary, and some places only see a high tide once every 24 hours. Those are called diurnal tides. So this is a daily occurrence, actually twice daily in most places. But tidal waves, even though they have the word tide in them pretty much, but without the E, they're not related to this gravitational push and pull. They're usually the result of earthquakes. So that's tides. Hopefully we avoided.
Yeah. Interesting character. All right. But ocean waves are not an easy concept. So what you see if you ever go to a beach, you know, that's the result of locations of the Earth, Moon, and Sun with each other in depending on the month. You're going to have varying waves. So Henry Cavendish took the law of gravitation and applied it to find the value of G, which we like to use, as well as Earth's mass, which was very big to do. And so when two masses, the distance between them and the gravitational force are known, Newton's law of universal gravitation can be used to find G. And so once the value of G is known, the law can be used to find the Earth's mass. So they found out that gravity is a field force. So gravitational field strength, which is our lowercase g we've been dealing with all year, is equal to force divided by mass. The gravitational field G is a vector with a magnitude that points in the direction of the F. And so as you see, it's all going towards the center of the Earth. As you get further and further away, you notice the arrows, as we used in vectors in chapter 3, the arrows, as you move further and further away, become smaller because the force that is exerted on objects farther away diminishes as you continue to move away from it. So, how do we apply the law of gravitation when calculating weight on a surface? So weight itself is mass times the gravitational field strength. Okay, so we get this formula here. But weight depends on the gravitational field strength. So weight changes with location. And so on the surface of any planet, the value of G as well as your weight will depend on the planet's mass as well as the radius. So that's why when you go to the moon, it has a much smaller radius and a much smaller mass than Earth. Your weight will change accordingly. So in order to find the gravitational force here, you're going to actually use the value of G times the mass of whatever planet you're on divided by the radius squared. Okay, that's your second formula. So let's look at the question here. We are to find the distance between a 0.3 kilogram billiard ball and a 0.4 kilogram billiard ball if the magnitude of the gravitational force between them is 8.92 times 10 to the negative 11th newtons. And so we know a few things here. And let me get situated here so I can do it on my whiteboard. We know the mass of object 1, the mass of object 2, and the force. We need to find the distance between them. So, lighten this up. So we are going to use the formula Fg is equal to G times M1 times M2 all over R squared. But this is what we are trying to find. So we have to rearrange the formula, and it looks like this. R is equal to the square root of G times M1 times M2 all over the gravitational force. And so now we can go ahead and plug in our numbers once we've got that. We have G, which is a value of 6.673 times 10 to the negative 11th Newton times meter squared over kilogram squared. Got a lot of, I probably set this up. I didn't set it up wrong. I just put it in the wrong portion of my whiteboard. And so we have 0.3 kilograms times 0. Yeah, I did. Divided by 8.92 times 10 to the negative 11th Newton. I'm going to move that over here. Okay. So when you place this in your calculator, which I'd like you to do so you can check my work, you should come up with 3.00 times 10 to the negative first meter. Oops. Is that what you get? Good. Okay. Now open up your books, page 242. Let's look at, let's see. Let's look at number 3. Okay. Number 3. And we're only going to do one of these examples of number 3 here. Number 3 says, find the magnitude of the gravitational force a 66.5 kilogram person would experience while standing on the surface of each of the following bodies. But again, we're only going to do Earth. Okay. All the other planetary bodies follow the same suit. You're just going to change mass and radius. Okay. So first thing is, let's list what we know. The first is our M1, which is 66.5 kilograms. M2 is the body in which we are on, which is Earth. So that's going to be 5.97 times 10 to the 24th kilograms. And we have to use the radius of Earth, since that's the planet that we're on, or the body that we're on. So the radius of Earth is 6.38 times 10 to the 6th meters. And just to restate it, our gravitational constant, 6.673 times 10 to the negative 11th newtons times meters squared over kilogram squared. So we're just simply trying to find the gravitational force, which in turn, by using this formula, gives us the magnitude, or it can relate to the weight, or I'm sorry, the gravitational force on this individual on this particular planet. So Fg is equal to G times M1, M2 over R squared. And since that's what we're trying to solve for, you go ahead and just plug in your values. Again, G was 6.673 times 10 to the 11th. Sorry, negative 11th. Newton times meters squared over kilograms squared. Times the masses. Again, 66.5 kilograms. I did it again. Times Earth's mass, of 5.97 times 10 to the 24th divided by the radius. Big numbers here, 6.38 times 10 to the 6th meters squared. If you can't read what this chicken scratch looks like, this says 5.97 times 10 to the 24th kilograms. So big numbers here. You will have to utilize parentheses unless you have a easier way for yourself. But don't forget your answer needs to be in newtons, since we're talking about force. When you calculate this, you should get an answer of 651 newtons. So double check your calculator on that one, just so you can make sure you're putting it in the calculator correctly. And that's going to be kind of what your homework's going to be like. So the good thing is you only have 6 problems. But as you can see, they're going to involve some big numbers to compute. I'm going to say what your homework is, and then I'll ask your questions. So for your homework, you're going to do questions 1 through 6. Okay? What's up? Oh, that's the second formula. Was here. So really what you can use is that is equal to that. Okay, who do I give one to? Just right. You do questions 1 through 6.